Hi, welcome to today's lesson. If you are in Algebra 2, this is section 6.3 in your textbook. If you're in pre-calculus, this is section 3.2. Our lessons are going to be together for about another 2 weeks, and then early May we'll be separating the two courses again. But let's go ahead and get started. We're going to do two main things today. We're going to do a little bit of review of the graphs of logs, and then we're going to do a whole bunch of examples of evaluating logs. So the first thing I'd like to do is I'd like you to give two equations for the inverse of y equals 2 to the x. Okay. X equals 2 to the y and y equals log base 2 of x would be two different equations for the inverse. So these two are the same as each other, and they're both the inverse of this one. To get this one, we switched x and y. To get this equivalent version of that, we used the base exponent other guy, the definition of a logarithm, to rearrange the three pieces. So what I wanted, and this one is y as a function of x. When we have y by itself, we say that it's solved for y as a function of x. Okay. And what I'd like to do is take you over to Desmos and just show you those graphs to reinforce that. So here's your y equals 2 to the x graph in red. And our exponential function, this is called an exponential function, it has a horizontal asymptote. If we graph the inverse, see x equals 2 to the y is the inverse. It has a vertical asymptote, and it is the same as log base 2 of x. And you can see that as I click back and forth, that this log graph here is the same as x equals 2 to the y. And they are reflections of each other over the line y equals x. They have that relationship. So what I would like you to do in your notes is take a moment and in your notes write down a little sketch. So just a rough sketch. I didn't, take out graph paper and plot points. But y equals 2 to the x should go down toward the horizontal asymptote, go through a y-intercept of 1, and go up very steep to the right. And exponential functions have a horizontal asymptote. I want to emphasize that today. Log functions have a vertical asymptote. So exponential function will have a horizontal asymptote. A log graph will have a vertical asymptote. And I threw the line y equals x in there as well, just to reinforce that we have that inverse property. Next, take a moment, please, and see if you can write an equation for the inverse of y equals e to the x with y as a function of x. So that means with y by itself. So for the inverse, if we switch x and y, I think that's not showing up so well. Let me grab a pen instead of a pencil. Okay. So for the inverse, if I switch x and y, I have x equals e to the y. If I then rearrange the base, the exponent, and the other guy using the definition of a log, I'll have y equals log base e of x. Since we have log base e, we're going to transfer that over to our special notation. Log base e gets replaced with ln, which stands for natural log. And this is what I was looking for. So this is the inverse of y equals e to the x with y as a function of x, with y by itself. This is also the inverse of y equals e to the x, but this one's not solved for y. So that's the one I was looking for. Let me take you over to Desmos one more time here and show you what these graphs look like. So this was 2 to the x from before. And if I graph e to the x, it looks very, very similar. Okay, they have the same shape, they have the same y-intercept, they have the same asymptote. So just like y equals 3 to the x and y equals 4 to the x and y equals 10 to the x all kind of look similar, y equals e to the x will look very similar as well. Let me get rid of those real quick. Okay. And then your log graph, this was your log base 2 graph. Okay, here, let me put it in blue. Okay, this was your log base 2 graph. And if I graph natural log, it looks very similar. They have the same vertical asymptote, they have the same x-intercept, and they have the same shape. The steepness is just a little bit different. So even though e is kind of like a weird new number for us, it looks really the same as it would with any of those other bases. So let me get that. Okay, so the red one is y equals e to the x, as shown here. The blue one is the natural log graph. And once again, the reflections of each other over the line y equals x. So one more time in the notes, because this relationship is so important, if we just make a little sketch, I'd like you to show that y equals e to the x looks just like 2 to the x and 3 to the x and 4 to the x. Y-intercept at 1, throw in that horizontal asymptote. If you have a different color, it's not a bad idea to show the inverse graph in a different color. The inverse will have an x-intercept at 1, drop down toward the vertical asymptote, very steep. And as it goes up to the right, not very steep at all. And that's your log graph, natural log graph. And they're reflections of each other over the line, y equals x. And one of the reasons I wanted to show you that graph today is because we graphed things like this by hand. So we graphed log base 2 and log base 3 and log base 4 and moved them up and down and left and right. But I've avoided the graph of natural log so far. But it looks the same and the transformations will work the same. The reason I've avoided it is because the numbers are not very friendly. So, if we look at this table here, if I were to do 2 to the x in my calculator, it'll make the graph we expect. I'm a little zoomed in right now. But here's the table. So the table is easy for us to make. We can do that with very little work. But if we wanted to graph e to the x, that is more complicated for us because even though the graph's going to look the same, so here's the graph. The only thing that's different is the steepness. When we look at the table, the numbers are very unpleasant. So 0 still gives you 1, but then everything else has these crazy decimals, both to the left and to the right of the y-intercept. So that's why we haven't graphed it by hand, because we don't want to try to make a table with these points. But I do want to inform you that the graph of y equals e to the x looks like all the other exponential functions, and the graph of natural log looks like the graph of all our other log functions. Okay, so that was a little bit on graphing that I wanted to do. What we're going to do next is we're going to get into a bunch of evaluating examples. So it might feel a little repetitive today, but I want to make sure you have enough of these examples in your notes before I send you off to practice them. So we're going to be evaluating without a calculator. And when we evaluate without a calculator, we did some of this 2 lessons ago. What we want to do is we want to name the third piece. So either x or question mark or your favorite variable. And we want to identify the base, the exponent, and the other guy. So if you want to find out what the log of 10 is, you want to realize first that log without a base means it's base 10. So log without a base becomes log base 10. This is what's inside the log. It's still what's inside the log. So this is my base. This is my other guy. And what we're looking for is the exponent. So if we change this around into base to what power equals the other guy, we can solve. By looking at this, 10 to what power gives you 10? That answer must be 1. Okay, next one. I have log base 5 of 1 over 25. Maybe you can try that one on your own. I'll use x this time to name that missing piece. Sometimes I use question mark, sometimes I use x. So this is 5 to what power is 1 over 25. We wrote in our notes 2 lessons ago that to make a fraction, we want to use a negative exponent. So the answer here is going to be -2 or x equals -2. -2 or x equals -2. Either way is fine. Okay. And you can always check it. You can show more work if you want to. So if you want to check it, you can show that this would be 1 over 5 squared, which indeed is 1 over 25. So the answer was the exponent. Next review problem. We want to find out what log base 8 of 2 is equal to. So it's 8 to what power equals 2. If you feel more comfortable labeling base, exponent, and other guy for every single problem, you can do that. I'm not always going to take the time to do that, but you certainly can pause the video, do those labels, and then jump right back in. So 8 to what power gives me 2? As we wrote in our notes 2 lessons ago, if you have a base and your answer is smaller, you want to try fraction exponents. And for the fraction exponents, there's no like solid rule for what fraction to pick. So what I would do is just try to the 1/2 first. Do you know the square root of 8? Neither do I. And then we could try to the 1/3. 1/3 power would be cube root. Do we know the cube root of 8? Yeah, it's 2. And that's what we wanted. So the answer here is 1/3. You can't just leave this. You do need to indicate what your answer is. So you can either write that at the end, or you can go back up top and fill that in. Lots of different styles to present your answer. Next one. And feel free to pause the video, rewatch any parts you want. But for students who are feeling comfortable with this, I hope it's not dragging. It's hard to do when it's hard to figure out the right pace when I'm not with you guys. So this one we want to solve, we want to evaluate, is natural log of e. So looking at that, natural log means that the base is going to be e. And here's what's inside the log. So if you prefer to put parentheses, that shows what's inside the log. So we replace ln with log base e, and then e is still inside. So this part here gets replaced with log base e. Log base e. And then we want to find out what that missing piece is. So my base is e, the missing piece is the exponent, and that comes out to e. So what exponent does e to that power equal e? That's going to be 1. E to the first will be equal to e. Okay. Continuing on with examples. Our next one is log base 4 of 1. Go ahead and try that one on your own. When you rewrite this in exponential form, you have 4 to what power gives you 1. The answer to that is going to be 0. 4 to the 0 is 1. And we had one of these problems in the past where the other guy here was 1. And some of you wrote in the comments in Edpuzzle, some of you asked if we're taking the log of 1, is it always going to be 0? Yes, that was a very good prediction you made. That is a property of logs that is going to be true. So whenever you're taking the log of 1, you're going to get 0 for any base that's allowed. So I used a here to represent any base that's allowed. The bases we're allowed to use are a bigger than 0 and not 1. And that comes from, if you remember where all this started, remember with our exponential functions that we couldn't use 1 because it wouldn't look like all the exponential functions. Exponential functions are supposed to look like this. If we did 1 to the x, it would just be that horizontal line. Remember with the exponentials that the base can't be 0 because you would get just half a horizontal line. And the base can't be negative. Do you remember when we tried a -2 in here? It went back and forth between positive and negative. So the restrictions on the base for the exponential were these. And since this is related to log, we have the same restrictions. You don't really have to focus on this part right now. I just wanted to remind you why this keeps showing up. It showed up in the definition, and I needed to write it with the property today to be technically correct. Okay, so the takeaway here is anytime you're finding the log of 1, you're going to get 0 as your answer. I don't think you need more examples, but feel free to write down if you have log base 2 of 1, that's going to be 0. If you have log base 5 of 1, that's going to be 0. If you have log base 1/3 of 1, that's going to be 0. And you can easily check any of these by changing to the other form. So for this one, identify your base, your exponent, and the other guy. 2 is your base, 0 is your exponent, and 1 is the other guy. So sure enough, that works. For this one, here's your base, here's your exponent, here's your other guy. So if I rearrange, sure enough, 5 to the 0 is 1. And if I rearrange this one, 1/3 to the 0 is 1. So it's not something you really have to memorize, but if you're aware of it, it's just a little shortcut for you. Okay, next one is log base 3 of 0. Want to take a moment and try that one? I'm going to use x this time for that third piece. Here's my base, my exponent, and my other guy. And our job is to figure out 3 to what power gives you 0. And I hope you didn't work on that one for too long because it's not possible. Sorry if I tricked you. You can't solve this. This is undefined. If you wrote no solution, that's fine. If you wrote can't be answered, that's fine. There's no answer to this. Log base 3 of 0 cannot be done. 3 to the x equals 0 cannot be solved. I have a couple of explanations for you for that. So we'll see which explanation you like. If you recall, when we first introduced logs, we had that the base had to be bigger than 0 and couldn't be 1. We also had this restriction that said x had to be bigger than 0. So that, I finally can explain that to you today. So here's one explanation why you can't find log base 3 of 0. Think of your graph of log base 3 of x. If you think of your log base 3 of x graph, it's going to look like this. It's going to have an x-intercept at 1 and a vertical asymptote at x equals 0. So when I ask you to find log base 3 of 0, what I'm saying is, if you think of this graph, what do you get when you plug in 0? Well, you can't plug in 0. The domain of this is 0 to infinity, not including 0. That's why when I gave you the definition of a log, that's why it had x greater than 0. Because if you look at the log graph, that is your domain. X greater than 0 is the same as this in interval notation. So that's why you can't find the log of 0. An alternate explanation that I think you might like more is that you can't solve this equation. So the reason you can't solve this equation is if you think of the exponential function. So instead of log, think of the exponential graph. Asking you 3 to what power equals 0 is asking you, when do you hit the x-axis? When do you get 0 for y? You don't, because that's where the horizontal asymptote is. And the range is 0 to infinity. So if I say, what do you plug in here? 3 to what power gives you 0? The answer is you can't get that. That can't happen. So you can memorize if you want that you can't take the log of 0, or you can think of your log graph and the domain. Or if you try to change it to exponential form, you'll see here that this can't be solved. So any one of those rationales or explanations is good to remember. Do you have some more examples? Okay. I'd like to throw one of these in. They put some of these in the book. You want to take a moment and try that? Okay. So the base here is 10. So because there's no base written. So this is called common log. When there's no base written, it's called the common log. And we assume base 10 because no base is indicated. So we have log base 10 of 0.01. And I always have a little trouble solving it in this format. But if I rewrite this as a fraction, it becomes much easier for me. So if we were to read this properly, it's 1/100th. So this is log base 10 of 1 over 100 equals what? So if I now rewrite it as 10 to what power equals 1 over 100, I can figure out pretty quickly that that answer is going to be -2. Because if I do 10 to the negative second, I get 1 over 10 squared, which is 1 over 100. Some of you might be comfortable solving it right from here. So if anyone, was able to do 10 to what power gives me 0.01, the answer is still going to be -2. I just have a harder time with it in the decimal form. I find that the fraction's easier for me to see personally. Next one. Evaluating log base 3 of 3 to the 5th. So what we have here is the base is 3, and what's inside the log is 3 to the 5th. If the parentheses help you see that better, then write them in. Name the third missing piece. I'm going to name it question mark. And what we want to do here is see 3 to what power equals 3 to the 5th. Well, the only way 3 to some power is going to be 3 to the 5th is if that power is 5. Here's our next one. So if we want to evaluate log base 3 of negative 9, we're asking ourselves 3 to what power gives me negative 9. See if you can answer that. And again, I'm sorry, kind of a trick question. You can't do this one. Undefined, no answer, no solution, you can't do it. If you're thinking negative 2, that doesn't work because that would end up being 1 over 9, not negative 9. There's no way to take a positive power, a positive base, and raise it to a power and get a negative. And once again, I can justify that in 2 ways for you. If we think of our y equals 3 to the x graph. So we're saying 3 to what power gives you negative 9? All right, so the question that's being asked here is, what do you plug in to get out negative 9? You can't. The range for this is only bigger than 0, so you can't plug in a negative. Another explanation is if you think of your log base 3 of x graph, what we're asking here is log base 3 of negative 9. So if you think of your log graph, we're saying, what do you get when you plug in negative 9? You're not allowed to plug in negative 9. It's not in the domain of the function. So you can't take the log of 0 and you can't take the log of a negative. You can memorize those facts, or you can always think back to your log graph. Or if you change to exponential form, you can think of your exponential graph. And remember, you can rewatch any portion of these videos anytime you want. So if something you want something repeated, you have the ability just to rewatch that part. The next few problems are only for pre-calculus. I'm going to not show these to Algebra 2. Since pre-calculus, this is a second time around for you. Since you learned this in Algebra 2, I thought it would be appropriate to throw a couple extra, maybe a little bit more challenging problems at you. So here's our next one, log base 8 of 32. We're going to go up to 14, by the way, if you're wondering how many more. Okay, so log base 8 of 32. So what we're asking here is 8 to what unknown exponent gives me 32? Now that might look kind of impossible to solve at first, because 8 to the first would be 8, and 8 to the second would be 64. So we want 8 to some power to give us 32. So if you look at what I just wrote down, this indicates that that missing exponent has to be between 1 and 2. It's going to be some fraction or some decimal. So to solve it, there's a few different ways. I'm going to show you the way I like to do it first, and then I'll show you a second way that I think you actually might like better. But here's how I think of it. What I do, if I know that I'm going to have a fraction as an answer, is I look at my base and I say, what do I know? What fraction exponent do I know for this? Do I know x to the 1/2? Do I know the square root of 8? No. So then I say, okay, well, do I know the 8 to the 1/3? Yes, 8 to the 1/3 gives me 2. Okay. Now I don't know 8 to the 1/4 and I don't know 8 to the 1/5. So I can run through all those and try them out, but I know 8 to the 1/3 gives me 2. Can I get from 2 to 32? Certainly, because if I do 2 to the 5th, I get 32. So if I piece that all together, what I have is 8 to the 1/3. What was 8 to the 1/3? It was 2. So we want to raise that to the 5th. So when you have a power to a power, you multiply those, and I get 5/3. The answer here is 5/3. And I can check that, and you probably want to check it because I said these were going to be a little trickier. If you do 8 to the 5/3, what we do, you learned this in Algebra 2 for sure. You do 8 to the 1/3 to the 5th. So it's the cube root of 8 to the 5th, and that's 2 to the 5th, and that is 32. So that's how I like to think of that, and that might work for some people. But just to give you another way to do it, the second way, some of you might like more. It's a little more structure to it. You can kind of memorize the process. So another way to do this is if you know you're going to have some fraction, because we know that exponent is going to be between 1 and 2, or if you're just looking at it and you cannot solve it, see if you can rewrite both sides to the same base. Let me make this exponent x right now. So I have 8 to the x equals 32. So try to rewrite with the same base. So 8 can be written as a power of 2, and 32 can be written as a power of 2. So if I rewrite 8 as 2 to the third, I have 2 to the third to the x. And if I rewrite 32 as 2 to the fifth, I'm going to be able to solve that for x. Because when you have a power to a power, you multiply. And what we have is we have 2 to the 3x equals 2 to the fifth. The only way 2 to the 3x is going to be equal to 2 to the fifth is if the exponents are equal. So I'm not dividing by 2. I'm just getting rid of the 2. The only way that this and this are equal to each other is if the exponents are equal. So I'm just equating 3x and 5. And if we solve this by dividing both sides by 3, you'll see that we get 5/3. So it doesn't matter to me which way you want to go about this. If you know your radicals and your roots pretty well, then you might be okay with this method. If you prefer a little more structure with an algebraic technique, then you might like this method better, where you try to rewrite both sides with the same base. Let me go ahead right now and give you another one of these, because this is usually the least favorite type of example. So let's have you try log base 9 of 27. Take a moment and try that. So you're looking for 9 to what power gives you 27. Okay, and no matter how you like to do this, you should get 3/2 or 1.5 would be fine for your final answer. So if you like a little more structure, a little more algebraic technique, you're going to rewrite both sides with a base of 3, because hopefully you recognize those as powers of 3. So 3 squared to the x equals 3 to the third. Property of exponents to simplify. And the only way these two are going to be equal to each other is if 2x is equal to 3. So we equate the exponents, set the exponents equal to each other, and solve for x. If you're very comfortable with your roots and your radicals, you might recognize that 9 to the 1/2 is the square root of 9, which gives you 3. And you can get from 3 up to 27 by cubing it. So if I take 9, that's my base, raise it to the 1/2 and then the third, then I'm going to have square root of 9 to the third, which is 3 to the third, and it works. So my exponent here is 3/2. You do not need to know both ways to do this. So if you really like this one, you never have to do this. If you really like this one, you don't have to do this. But if you want to, work with both, that's great. But you just need one way to solve it. Okay. Next problem. Next problem is log base 9 of 1/3. Take a moment and try that. The answer you should get is -1/2. This may not happen instantly in your head. You might go through a thought process, and you can write down as little or as much work as you need to. Some people might get this immediately in their heads. But when I look at this, I say, okay, there's two things going on. I need to get the number 3, and I need to make a fraction. Well, I know how to change 9 into 3 with an exponent. I can use the 1/2 exponent to change 9 into 3. But I don't want 3, I want 1/3. So to make a fraction, use a negative exponent. So that's how, so to get that smaller number, I use a fraction exponent. So that's how I picked 1/2, and use a negative exponent to make your answer a fraction at the end. And that's in notes from 2 lessons ago. You're going to get more practice on this in the next day or two as well. Next one is natural log of e to the third. So for natural log of e to the third, we start by replacing ln with log base e. So this is natural log, and what's inside of it is e to the third. We're going to replace ln with log base e, and e to the third is still inside. So this one is e to what power gives me e to the third, because my base is e. My exponent is question mark, and this is my other guy. So my other guy is e to the third. My other guy has an exponent in it. So e to what power gives me e to the third? That power must be 3. This should look similar to number 8 from our work earlier today. When we did number 8, we used a base of 3 instead, and here we're using a base of e, which always looks a little more confusing. And here comes our last problem for today. Last problem for today, pre-calc. Here we go. I'd like you to figure out, please, what the natural log of 1 plus log base 2 of 16 plus log of 100 is. Take a moment and try that on your own. And if you get really stuck, don't worry. I'm going to show you the solution in just a minute. Your final answer should be 2. And here's how I go about solving that. You want to treat each of these as 3 little problems. So if anyone was trying to identify like a base for the whole problem, you can't, or an exponent. If anyone tried to set this equal to question mark and then tried to rearrange, it's not going to really work for you because you have 3 different bases. So what you want to do instead is think of this as a problem. We may have actually done this one earlier today. Oh, no, we didn't. Okay, so natural log of 1 is log base e of 1 equals what power? Well, that power is 0. So natural log of 1 is replaced by 0. And then solve log base 2 of 16. This is saying 2 to what power gives me 16? That answer is 4. So I'm replacing that with 4. And then I brought down the minus. And the last one here is log of 100. Log without a base is the common log. It's assumed to be base 10. So we're asking here, when we ask for log of 100, 10 to what power gives me 100? That exponent is 2. So I'm replacing log of 100 with 2. So I replace this with 0, keep the plus. Replace this with 4, keep the minus. Replace this with 2, and I get 2 for my final answer. Thank you for watching, and you guys will get plenty of practice in the next couple days.